evening. Today I will conduct your NPTEL week 12 problem solving and doubt clearing session for the network analysis course. And today we'll be focusing majorly on the op-amps, which has been taught in week 12. So I'll be telling some brief theory about the operational amplifiers, as well as then I will be solving some problem sums from the previous year's assignment. So let me share my screen. So today is week 12. And today we'll be considering operational amplifiers. So op-amps. So basically op-amps. So when we think of an op-amp, what comes to our mind? So the symbol of an op-amp is given by negative plus. You have your plus VCC minus VEE, and this is your V out. Okay, this is your V out. So how do they work? Like how does an op-amp work, or what are the principles of its operation? So this is your Vn minus and this is your Vn plus. So these are your signals which is coming. And okay, we will consider one example IC. So when you will practically use op-amp in your so Akash, I was just telling about op-amps. How we have an op-amp symbol is given like this, and you have two input terminals, V input minus V input plus, and you have an output terminal. You also have a plus VCC, which is, and a minus VEE. These are for biasing the op-amp. Now, so for this IC to work, it requires some power, and that power is given by this plus VCC and minus VEE. So when you will be using an op-amp in your, so first of all, op-amp is very important. It is used in many applications, like as a adder, subtractor. It can be used. It can be used as a filter, low pass filter, high pass filter. It can be used as a compensator. It can be used as a controller, and it can be used for sensing. It can be used to convert current signal into a weighted signal, and all these various features are possible using op-amps. So op-amp is built based on various structures or various amplifiers connected to give it some particular characteristic which is very useful. Okay, so once they made an op-amp, it will be sold as an IC, as an integrated chip. So the chip will come out like in this form. Okay, 1, 2, 3, 4, 5, 6, 7, 8. This is not uniform. It's not drawn to size, but this is just a rough example. So we have pins. So there will be this pin. Okay, this pin means what? This is your pin number 1. So this pin number 1, 2, 3, 4, 5, 6, 7, 8. So this is the identification mark for you to know that this is pin 1. Otherwise, it will all be symmetrical. So you will not know which is what. Okay. So this is for pin 1. Then further case is uh, for there's a very useful IC which one which is used widely is the LM741 IC. In this one, pin 1 is not used. Okay. Pin 2 is Vin minus. Pin 3 is Vin plus. Pin 4 is minus VEE. Pin 7 is VCC. And pin 6 is V out. Okay. So there is an 8-pin IC. You're going to go in the market, you say you want to open, you want LM741. He will give you this sort of IC chip, he will give it to you. And it can also, so it can come in various sort of packages. That is, it can have holes, like it can have these sort of lines. So this, or it could be of a form tapered. Like what I mean to say is, its leg can be something like this. Sorry, its leg can be something like this. So when you connect it, it will be like this, or its leg can be something like this. There are various ways it will be there. But the end goal is you have 8 pins are there. All right, plus VCC and minus VCC. And okay. So why do we need this VCC and VE, and how much value do we give for them? What is the voltage range?
Those are working voltages when varies from plus 12 to plus 50
Okay,
in case of VCC.
okay, all right. Yeah. So now let me consider an example circuit. Uh, this is your op amp minus plus. mm, And you have some sort of resistors you have over here. This is your plus VCC. This is your minus VEE. This is your V out. Okay. And over here, you connect some inputs. Let me first. So this plus VCC, how will you give a plus VCC for in your actual circuit? How will you give this plus 15 volt or plus 12 volt?
To that pin, right? Whatever you mentioned.
So
7
you,
or 8.
yes. So you will require a voltage source. Like you require a power supply, right? You
Yes,
would
sir.
require a power supply. And that power supply should generate some plus 15 volt. There will be some ground of the power supply as well. Okay. And this is assumed your ground, and this is your minus 15 volt. Okay. So this plus 15 will go to VCC. This minus 15 will go to your minus VV pin. Where will your ground, what will happen to your ground?
Ground. Sometimes we'll ground that based on the chips. I mean, IC will ground it, or we'll use minus VEE, right?
No, you have to connect ground. In the circuit, the ground is to be there. Ground is like a reference point. Okay. So basically, this is connected to your plus minus. This is assumed as your ground. Okay. So this is your 15 volt. This is your minus plus 15 volt. Okay, and this is your ground. So effectively at minus V, you are going to get minus 15 volt with respect to the ground. At VCC, you will get plus 15 volts with respect to the ground.
Okay.
Hmm. So this is for biasing your op amp. Now you will also have some certain signal, like let us say you have some, this also you have your signal A, you have your signal B. All of them are with respect to ground. So all this ground, all have to be connected. You have your V output and there's some load. That also has to be connected to the ground. Okay. So the
Yes, sir.
grounds, all the grounds have to be connected in your in whatever you're making, your breadboard or in your Vero board or in your PCB. Hmm. All the grounds have to be connected. That is, so your ground is acting like a reference point. Okay. So have you used an op-amp?
Currently, I'm just learning about it.
Okay. What about Bharat?
Mm,
Bharat Srivastava? Okay, so currently what you're learning about op-amps?
I have a subject called linear integrated circuits, and there we are learning the operations and its applications.
Hmm. Okay.
Uh,
So they what are all applications they have taught to you?
it has wide range of applications, like everything based on what we are going to use,
Mhm.
right? Op-amp has a vast amount of applications, one or two maybe in amplifier circuits or filters it may be used in.
Yeah, yeah. Filters just white noise.
Yeah.
Okay. So now we have to consider one thing. What is the input impedance of your op-amp? How much is it?
Sorry, infinite.
Input impedance is infinite. It tends to infinity. Okay. So why is it there? Like, is it good or bad?
Current flowing inside the op-amp is zero. That's why input impedance is infinite.
Okay. Okay. That is one reason. So input impedance is infinite. What is the gain? What is the gain of your op-amp?
So A times V1 minus V2.
So what is the so gain? Your V output is A times V plus minus V minus. Okay.
Ah, yes, sir.
So this is your gain. A is your gain, right?
Yes.
So what is the value of this gain? Hmm? What
Depends, right?
depends on what?
V plus and V minus.
Like how? Like op-amp is a linear device, right?
Yes.
Okay. So ideally the gain should be infinite, but it isn't in reality. This is your gain. Third one is output impedance.
Output impedance is zero.
Okay. And why is that? What could be the possible reason? Hmm? Okay. So these are the desirable characteristics of the op-amp, and to a great degree, it satisfies it. Right. Now, one more thing is, what is the characteristic of op-amp? Assume in your x-axis it is V plus minus V minus, and over here it is V output. Okay. What
It
will
is linear for some point and then it is just
okay? So it is linear.
direct.
Assume it.
For some.
Uh, then it will
And then till
Then?
that voltage, the provided voltage, supplied voltage.
Okay. So,
Then it is direct.
so this is your plus VCC. This is your minus.
Yeah, minus VEE.
Okay. So ideally the gain of the op amp is infinity, but then there's this slope, and this slope is your actual finite gain. This is your finite gain. So if your A tends to infinity, then it will look something like this. This is your V plus minus V minus. This is your V output. If the slope is infinite.
I said it depends on V plus and V minus just because V plus and V minus we are deciding and it is 0, right? The difference between VCC and VE.
Yeah, you want your V plus and V minus, the difference to be in the range of VCC VE. That is true. But in the usual sense, it is like gain is approximately some linear value A. It may not always be true, but it is desirable, or it is approximately true that the gain is some value A. Okay.
Yes.
So now, this is one case. Now, let us assume time t. This is your V plus minus V minus. Okay, it is changing like this. How will your V output look like? This is your V minus. This is your V plus. This is your plus VCC. This is your minus VEE. This is your V output. And they have told that the difference of V plus minus V minus is a triangular wave. How will your output look like?
Not sure.
Okay. So, you know your V output is A into V plus minus V minus, right?
Yes, sir.
So, you will assume that if that relation is true, and it is true, this will be like same. It will also go like this, like this, like this, like this, like this, right? It will just be, suppose this is a had value of 1 and the minus 1. This will have value A and minus A, right?
Yes. Sir.
Because you know V output is A into V plus minus V minus. But if I tell you, assume this was like this is approximately 1 millivolt, okay? And your gain A is like 10 raised to 5. What will your V out then be?
So what is that 1 millivolt?
This is your
V plus and
1, like this. The amplitude of your triangular wave is 1 millivolt. Okay.
yeah, it will be very high, right?
Yes.
10 to the power 5 will be the amplitude.
So it should be 10 to the power 5 into
1 millivolt.
volt. How much is that?
10 and 100.
So it'll be 100 volts. Is it possible?
No.
It is not possible. So instead, mm, you will get a wave like this. Mhm. So this value is your plus VCC, this value is your minus VPP. Okay,
Yes.
sure. So this is how it is. Now in this case, it is working as a comparator. Hmm? In this application, it is working as a comparator. So are there any queries till now?
No, sir.
Okay. So let's start with this.
So in that IC, which you mentioned, the other pins like five, other pins like 5 and 8, if I remember right. What will they be used for?
So this 1, 5, and 8 are NC, no connect. They don't have any function.
They'll be simply there.
Yeah, they are simply there.
Okay.
So the reason is like in an industrial application, you have certain sizes. Okay, like you assume for shoes, you have size 10, size 11, size 12, right? So the manufacturer knows that he has to get it into this size 10, size 11, or size 12. Then only someone who's buying knows that they want size 12 and they want it of that size. And so he can make it and he can sell it. Now for an IC and all, they have some standard packages, like an 8-pin package or a 16-pin package. All those packages are there. So to fit this IC, he will use a 8-pin package, such that, you know, what when someone is manufacturing something, he should manufacture it in such a way that it can be used by everyone easily. And suppose I am manufacturing a, okay, let us say I'm manufacturing a TV. Okay, so it should not be like my TV requires some very different setup than everyone else's TV. So if I had one TV of company A and then I'm buying a TV of company B, it should not be that company will be set up and all the requirements for it are so drastically different that I have to spend a lot of money to modify the various setup, etc. Okay, so that is not feasible and that is not a good way to do business. So similarly, when these manufacturers they make, there are some certain standard pin counts, some standard pin packages. Like they know that all manufacturers make it of 8-pin in this package. So then they will also fit their IC in that similar package. And so 2 pins are like of no use. In 3 pins are of no use in this scenario.
Okay. Understood.
Yeah. So yeah. Then means okay, one more concept is for op-amp minus plus. This is your V minus, this is your V plus, this is your V out. Okay. So and this is your plus VCC and your minus VEE. How much is the current which will flow into the op-amp?
Zero, right?
Okay, so current flowing into the op-amp is 0, right?
Yes.
Now, we also know that your V output is given by A into V plus minus V minus. Okay, assume my gain A is 10 to the power 5. Okay. My output voltage
Yes.
which I am measuring is 1 volt. Okay. So what do I get? My V plus minus V minus is actually equal to V output by A. What is the value of that?
So 10 power minus 4.
It will be 1 upon 10 to the power 5. So it is approximately 10 microvolt.
Okay.
So that means suppose V minus is equal to Vx, some voltage, and your V plus is Vx plus 10 microvolt. This has to be satisfied, right? Because that then only your V output will be 1 volt. So you could say that V plus is approximately equal to V minus because 10 microvolt is a very small value, right?
Yes.
So this is a concept of virtual ground. So you could say that the voltage at the negative terminal is equal to the voltage at the positive terminal, approximately equal to the voltage at the positive terminal. So what are your doubts in this? Because this is a very confusing thing. You can ask your doubts.
Sorry, I got disconnected once. Can you just repeat what you mean?
Okay. So till here it is clear V plus minus V minus is 10 microvolt.
Yes, sir.
Okay. So assume your V minus is some voltage Vx. Okay.
Okay.
Then your V plus is Vx plus 10 microvolt.
Yes, sir.
So I can approximately write that my V plus is approximately V minus, which is approximately Vx. Okay. Because 10 microvolts is a very small value.
Yeah, yeah.
So then I can assume, like it's a good engineering approximation, that my V plus is equal to V minus. Okay. That whatever is the voltage
Yes.
over here, whatever is the voltage over here is going to be the voltage over here as well. I can make this approximation and this assumption and I can solve my sums. And this assumption is known as your virtual ground concept.
Yes.
This is your virtual ground concept. So when we solve sums, this concept is very useful and which is needed when you are solving sums. Correct?
Okay.
Okay. What about others? Others have any queries? Bharat, Suresh Babu? Okay.
Sir, no doubt.
Oh, I've not seen you for a while actually,
Okay.
Suresh.
Sir,
Huh?
sir, tell me, sir. Sir, fine, sir.
Yeah, because I haven't seen you for a while. So I was asking.
Due to the some work, sir.
Okay. Right. So now we will.
Sir.
No, it's fine. It's fine. So now we'll start solving sums. So assume this sum. Okay. Okay. So this is your sum. And they're asking you to find what is your V output in volt. Okay, what is your V output? So what have they given you?
So op amp, right?
Okay, okay. Actually, mhm. Then
V1 and V2 are given. The supply voltage is given.
mhm.
They are asking output voltage.
They're asking output voltage. So okay. So you know
Here node voltage is 3 volts. Virtual voltage.
your voltage V plus is 3 volt. Okay, that is given. So
Yes, sir.
what does that mean? This voltage over here, that is V minus,
Node voltage.
it be also equal to 3 volt.
Minus of minus plus 6 volts.
Mhm.
Here applying KCL. Sir.
Okay, now I'll apply KCL. Let us apply KCL where
3
where
minus
will
3 minus minus of minus plus 3
V minus
divided by 4.
V minus minus of
Minus of minus
Y minus of minus.
plus.
Huh?
Actually, I'm taking 3 volts is positive. Node voltage is taking positive.
No. Okay.
V plus. Actually, I'm taking V plus is taken positive.
V plus is positive. That is 3 volt.
V plus minus. Here I am taking.
Okay, okay. I'll go step by step. So assume the voltage over here is V minus. Okay. So I apply KCL at this node. What is the current flowing over here?
0.
This current is 0. So the current flowing over here should be equal to the current flowing over here. Huh?
Yes, sir.
So that means this one. So what is this current? This current over here is actually 3 minus of V minus upon 4 kilo ohm, right?
Yes, sir.
Yes, sir.
That is equal to current flowing here. And that current is how much? V minus
3 minus V naught. V minus
Minus V naught
V output.
by 2 kilo ohm.
10 to the power 3. Okay. Now, what is your V minus?
Minus 3 volts. No, sir.
Yeah, that's my question. Why V minus is minus 2? Because we already have V plus is equal to 3 volt, and V plus should be equal to V minus by virtual ground concept. That means my V minus should be equal to 3 volt, right?
Okay, sir. Rightly.
So if my V minus is 3 volt, this will be 3 minus 3 upon 4 into 10 to the power 3 is equal to 3 minus V output upon 2 into 10 to the power 3. Okay. So this will be 0. This is equal to 3
1.5
output.
millivolts.
V naught equal to 3.
So you will get V naught is equal to 3 volt.
3 volts.
Okay. So let us. So now we have got the answer. How do I look at the circuit again and try to check whether it is correct? Now we know over here voltage is 3 volt. That means voltage over here also is 3 volt. If voltage over here and here is 3 volt, then this current is 0, right? If this current is 0, that means this current is 0.
Yes.
That what does this mean? This voltage drop is 0. That means your V output is equal to 3 volt. Okay. Any queries in this?
But that 3 volt is due to that V plus 4.
That is due to this and due to this, both. Due to both of these power supplies. That's
Which
why
end?
it is due to this as well as this, both. Both combined are resulting into such a condition.
3 volt. Oh,
It is not like this 3 volt is only because of this. It is because this is 3 volt and this also is exactly 3 volt. That is why no current is flowing and so V output is 3 volt. If there was any deviation,
yes.
then the V output will change.
Okay.
Okay. Now we'll go to any question. Sorry. Today is actually a bit late. So this is your question. Now, how will you solve this? What should I do in this case?
Firstly, there is no virtual ground concept. Yes, voltage.
Why?
There is no voltage provided to the V plus terminal.
So,
You said it's only applicable when both the V plus and V minus should be equal.
no, your virtual ground concept is applicable, right? But why is it not applicable? It's my question. Okay, we'll assume it is applicable, right? Let us assume it is applicable.
Oh, okay.
So, what is your V plus?
0, right? Is connected to the ground.
Yes, it is 0 volt. So your what should be your V minus?
It should be 0.
It should also be 0 volt. Is it 0?
That we don't know.
We don't know. But by virtual ground concept, it is approximately 0. We can approximate it to 0. Okay, we approximate it to 0. And in our calculations, we use it as 0. Okay. Now, what should we do? I've got this be approximately 0 volt. How will I get V out?
Again, at that node, we can apply KT.
Okay, so again we apply KCL.
Other case.
This is one current, this is one current, and this is another current, this another current. So what we will get? What will be this current flowing? What will be the expression for that?
1/4K.
1 minus 0 divided by 4.
0/4 kilo. Yeah.
Okay.
Plus
Then
4/3 into 10 to the power 3.
okay. Then
0 minus V equals to 0 minus V naught by 2 kilo.
okay. Then
That current V minus
that
0
current
minus.
is 0 because no current can flow into the input
Ah,
of
no
the.
current. Yeah.
So then what do we get? 1 upon 4 into 10 to the power 3 plus 4 upon 3 into 10 to the power 3 is equal to minus V output upon 2 into 10 to the power 3. So we get 1 upon 4, 4 upon 3 is equal to minus. Okay, so calculate what will be your V output?
So one second.
What will be your V output?
Minus 3.166.
Okay. So your V output comes out to be minus 3.1667 volt. So is this correct?
That we have assumed that there is a virtual ground.
Okay. So if you look at this circuit, at the positive terminal you have 0 volt. At the negative terminal you have some voltage. It is some voltage you are looking at, right? It is not exactly 0, but it is some particular voltage. Hence, your V plus minus V minus is less than 0. So what are you getting? Your V output, you're getting it to be negative. It's minus 3.1667 volt. Okay. So this virtual ground concept actually is applicable. It is applicable.
Okay.
Okay. So now we'll go to the next question. Okay.
So if V plus is less than V minus, then V out will be in negative.
Yeah.
Can you say that? Yes, I just want to ask that.
Tell them.
Yeah, it always will be like that, or it depends.
At your V plus terminal means at this terminal and at this terminal. That difference decides what will be your V output. Okay. That's how
Okay.
all happening internally, everything, etc. It's like a it's like a feedback. It will try to adjust such that this is approximately equal to this. And the result in that
Ah,
you get some particular output voltage is required.
okay.
Yeah. Now let's go to the next question. Okay. So how to solve this?
Again, we can apply KCL.
Okay. So again, we assume virtual ground concept. And one thing to keep in mind is because you are feeding back the output voltage signal at the negative terminal of your amplifier. So there is a sort of negative feedback. And you guys have studied feedback?
And not a lot, but yeah, we are just touching.
Like in what have you studied?
So I know a simple concept that feedback is given, and if it is given in the negative terminals, negative feedback, based upon that feedback which is given, the amplifier will be adjusting its output voltage later on.
Okay. So in a common sense perspective, like suppose you are telling or giving a speech or something, and then someone listens to that, and then they come and tell you after the speech, or while you are telling your speech, you observe that they are not interested or they're sleeping, then you know you're getting feedback that what you're doing is not proper. So when you get a feedback that what you're doing is not proper, then you will, you will make some changes. You will talk, tell a story probably, or talk louder, or say something interesting, right? So that is how you are
Yes.
adjusting. So that's how feedback works. And negative feedback is very useful. It's like a concept you will find almost everywhere in your electrical networks, like in your electrical topics for a system level concept, because it is like stabilizing, will improve the stability. Okay. It's not always true, it will improve the stability, but it is a way in which you can sort of regulate and control your output. So open loop is not always good. You need to have closed loop in many applications. Okay. So now in this case, we will apply virtual ground concept because the output voltage signal is being fed to your negative terminal. So we can apply virtual ground concept. So this is your V plus, this is your V minus. So can you tell me what will be your V plus? What is the magnitude of, how will you solve this? Because when you look at it, it looks so complicated, right?
Yes, sir.
So how do you solve it? What to do?
We are solving
Apply
from
the potential divider rule.
Okay, where will I apply potential divider rule?
Set a V plus terminal.
Okay, so I'll apply potential divider rule as Bharat is saying. V plus is what?
2 into 3 upon 4.
2 into 3 kilo ohm, 1 kilo ohm plus 3 kilo ohm. So that is equal to 2 into 3 upon 4. And how much is that?
6 by 4, 3 by 2.
That is 1.5 volts. So I get V plus is 1.5 volt. That means what is my V minus?
So V minus is also 1.5. If you apply potential divider rule, also we will get 1.5.
Okay. So what do you mean potential divider where? Where
We
did you
still
apply
don't know
potential?
what we know.
Potential divider नहीं लगेगा.
Over here you cannot apply potential divider, right? Because the
Yes,
V
sir.
out
Yes,
is
sir.
on ground.
Ah.
Okay. So what do? You apply KCL. So when you apply KCL, what do you do?
V minus by 1 kilo.
V minus.
3 minus V minus.
How you do
We are
V
applying
minus?
KCL at V minus.
Okay, I apply KCL at V minus here. Okay, let us see.
And this
Apply
is an
KCL
incoming
at,
current, and
so this is incoming current, this is incoming current. Where's the outgoing current?
to that
3
1
minus
kilo ohm.
V up.
Okay. Okay, Bharat, you're saying something?
3 minus V upon 1, that is equal to V minus V0 upon 1.
Yeah. Right now, Akash, this current
Yes,
is equal to this current. This current is equal to 3
yes, sir,
minus
yes, sir.
1K. And this is V minus V output by 1K. So this becomes 1 kilo, 1 kilo it cancels. So this is 3 minus V minus is equal to V minus V output. So your V output is equal to V minus plus V minus 3. What is your V minus?
1.5.
So it becomes 2 into 1.5 minus 3. How much is that?
3 minus 3, 0.
So it is 0 volt.
Yeah, 3 minus 3, 0.
Uh, so any doubts in this?
No,
So
sir.
if not for that voltage divided rule,
Hmm.
what is the way to find that V plus?
No other way. According to me, there's no other way. Because
Oh,
this current will be 0. So that's why you can apply
yes,
voltage divider rule with confidence. Hmm.
yes.
Okay. So now we'll go to next question. So how will you solve this sum? How will you solve it? Okay.
Will that 1 kilo ohm and 6 volt have any shape
Have any?
role to play in V naught?
Yeah, you tell me. So we must consider, we must think.
Since there is voltage connected, they might have.
Okay. Possible. So till now, how are we solving the sums? What we used to do?
We used to find V plus and V minus.
So what is your V plus here?
And then through the V plus will be 3, right?
Huh?
Minus 3.
Y minus
Minus
Y.
3 minus V plus divided by 0 will be equal to 0.
What?
Correct.
What is the
Alright.
voltage over here with respect to the ground?
Plus 3.
That is 3 volt, right? If this is 3 volt, what is your V minus?
Will be 3.
That also is 3 volt, right? So now this is your V minus. This is also your V minus. Now how will I sum?
V naught will be equals to this two current. I mean the current. If we apply KCL at V naught,
Okay, apply KCL and we know what I did.
V naught. Sorry, V minus
What is V?
3
Okay, your V minus
minus V naught
minus V naught
by 4 kilo ohm
by 4 kilo ohm.
plus this will be equal to V naught. Right?
This equal to
I'm not sure about what to do with that 6 volt.
okay. So that 6 volt is confusing us. What I know
Yes,
for certain. Okay, what I know for certain is I know virtual ground concept is poles through. So that means this is 3 volt, that means this also is 3 volt. Okay. What is the current flowing in here?
0
What is the current flowing in here?
will be 0.
What is the current flowing in this?
Which one, sir?
What is the current flowing in this 5 kilo ohm resistor?
Will be the current coming from V naught.
But I know the value, no? What is that value I'm asking?
So 3 by 5 kilo ohm.
Yeah, so current
Yeah.
5 kilo ohm resistor is V minus by 5 kilo ohm. So that current is actually 3 by 5 into 10 to the power 3. That comes out to be 0.6 milliampere.
Milliampere.
Okay, 0.6 milliampere, I got it. So this is my current I. What is this current?
Point
Which is
6.
coming from V.
Sir, apply KCL 0.6 milliampere.
This also is current I only. Because all the current flowing like this is going over here. No current is going here. This current is 0. Right?
Yeah, through that 4 kilo ohm also this will be
Okay.
0.6.
So then what is my
Yeah.
output voltage? Output voltage is a current I into what? My 4 kilo ohm plus 5 kilo ohm. Right?
Yes.
So what is my current 0.6 milliampere, 0.6 into 10 to the power minus 3 into 9K, that is 9 into 10 to the power 3. How much is this?
5.4 volts.
This is
5.4 volts.
volts, right?
Yes. So we don't need to consider the 6 volt to 1 kilo ohm.
It is not coming to the picture in this case, right?
Yes.
All right. Now let's go to the next question. Okay, so which is my question 5. Now how will I solve this?
Minus 6 volt,
Well,
V0 minus 6 volt.
and how did you come up with that answer?
There is a potential divider over there, right? V0 into 2.5 by 7.5. So if we
Okay.
know that voltage across 2.5K, then it is easy for us, potential divider, right? So negative terminal is 1 volt, 1 volt minus 3 volt. So it will be like minus 2 volt at across 2.5K.
Okay.
I know V0 by, it is V0 by 3, right? So V0 by 3 is equal to minus 2 volt. So V0 is equal to minus 6 volt.
Okay. Yeah, you're on the right track and correct. But whether others have understood is the question. So Akash, Bharat, did you understand?
Sir, can you just repeat what he said?
Okay, so what he's saying is the voltage over here, this is V plus. Your V plus, you know it is 1 volt. Your V minus, you know it is equal to plus 1 volt. What is the voltage over here?
1 minus 3.
The voltage over here, assume Vx. How do you get that value? You, so over here it is 1 volt. So over here it is actually acting as a virtual plus minus 1 volt is over here, right? And this is your virtual ground. This is your ground. So when you apply KVL over here, okay, you apply KVL. You get 1 minus 3 minus Vx is equal to 0. So your Vx is equal to minus 2 volt. Is this fine?
Yes.
So I got Vx is minus 2 volt. Now by resistive divider rule, what do I know? I know Vx is minus 2 volt and my Vx actually is V output into 2.5K divided by 7.5K. That is Vx into 2.5 divided by 7.5. So it's a V output. So your Vx is actually V output into 1 by 3. So your V output is 3 into Vx. How much is that?
2
minus 6.
It is
Minus 6.
into minus 2, so it is equal to minus 6 volt. Right?
Yes.
Now,
So what are these rules we should look for when we are just solving? This is a pretty normal question, but somewhere in the previous question we just used current divided rule.
basically you must apply virtual ground concept because there is negative feedback. Once you apply virtual ground concept, then you have to apply should be KVL or KCL. That is the trick.
Sorry, what?
First, you have to apply virtual ground concept.
Yes, sir.
Once you apply virtual ground concept, then you have to apply KVL or KCL as required.
I know, sir. I am not asking for this specifically, but by seeing patterns, you guys are noticing something, right? Which I am not until now. So that's what I'm asking. What are these? Maybe I'll get it when I solve so many questions. But what are the things that I should look for? Basically, I'm just asking that this rule will be applied. What are the rules we would describe that I should know? Current divided,
yeah,
current
division rule
current
is
division rule, voltage division rule is the thing, and then
these
what else?
virtual ground concept is required for op-amp specifically, right?
And not only for op-amps, for any network, any such.
Network and all, it becomes wide, it becomes broad. It becomes broad. So basically, you can practice it, and at least for gate exam, like this is what I was advised this. You should come to a state where you look at the question and you know that I have to use this method, I have to apply this formula, and this is the formula which I have to use. So, like, just look at the question and you directly know what you have to do exactly with it. So,
Yeah, I saw some network questions from that I don't remember exactly this year gate or last year, and I just started solving in KCL KVL. I got the answer, but it took some long hours. Then I just checked the answer key. It was like I just apply current division rule for this to just a one step answer. I was like,
because at that time you require speed now.
yeah. That's what I'm asking. What are these things that I should remember while solving this kind of questions?
Yeah.
I think I.
Voltage division. Yeah. And you're saying something?
I know, sir. It was like 2-3 questions I solved. I got the answer finally, but it took so long hours. But
Yeah.
as you said, the current division rule came into play, and it was like 2 to 3 lines they just wrote the answer.
Yeah. See, current division rules, voltage division rules, these are very basic. And those you should know it. And even if you don't know it, you should be able to derive it and verify. So many times, you know, the formula should be in some particular manner, but you're not sure and not confident. Then you should be confident enough to derive it to know that, okay, this is the way it is. What I thought is the correct answer, correct formula, etc. That is worst case. But it is desired or it is recommended that you should know the formula by heart. You should know when to use the formula, under what circumstances, under what conditions, and what clauses are there to keep into mind to use the formula. And for that, basically practice is all that you can say.
Yeah. I just want to know that this is a thing.
Yeah, and like for gate and all, if you're giving, you must just basically focus on the high weightage topics. And it's not like you can complete study every topic and you can go through every book, etc. It's not possible. So it's like if you're using some classes notes you go through it once, then you go through it twice, you go through it thrice. So as you go through it the second time, third time, you should reach a level that you look at the question and you should know, this is the way to do it. That way. So
Yes.
also, like, sometimes these sessions I usually don't do it, but in the previous year when I conducted NPTEL sessions, like, I used to try on some occasions I used to give a brief recap. Like, I will say that this is the sum. Then for what I did was, first we did resistor divider, we got a potential at V plus. Then what I did at the V minus node, I did KCL applied, and then I got the answer. So 2 steps, right? So if you see all of our sums, you first find V plus, and then you do KCL at V minus, you get the answer. Okay.
Yes.
Even over here, it's the same. And in this case, you got confused, right? You got confused. So
Yes, sir.
keep in mind, you got V plus. Now V minus you have to apply KCL at V minus. What mistake you did was you tried to apply KCL at V output, and that got you confused.
Yes, sir.
So if you applied KCL at V minus, then you would not consider, you would not care like what is the V out, what is the 6 volt, what is the 1 kilo, because it doesn't come. The thing is, you have to find V plus, you have to apply KCL at V minus, and then you're getting your answer. So that's how you must look for patterns, like which pattern is recurring, which pattern is used a lot. Then it will make the solving the sums easy.
Yes. Thank you.
Yes, and you were saying?
I just thank you.
Sorry?
I just thank you.
Okay. So now we have did some question 5 we did. Now question 6. So now over here, what should we do now?
KCL at positive node, we can apply.
We apply KCL at V plus. Okay.
Yes.
So how will we do?
V0 minus 3 by 5 plus V0 minus 4 by 5 equal to 0.
Okay. So first thing is you must know that V minus is actually equal to V output. Right? This node and this node are the same. It is shorted. Then you know your V plus is equal to V minus based on your virtual ground concept. That means your V plus is actually equal to V output. Now I apply KCL at V plus. Now I do KCL at V plus. When I apply KCL at V plus, what do? I consider that both the currents are going out. Okay, both the currents are going out. So I have V output minus 3 divided by 5 kilo ohm plus V output minus 4 divided by 5 kilo ohm is equal to 0. Right?
Yes.
So then I get V output minus 3 plus minus 4 is equal to 0. So what will be my V output?
3.5.
So my V output comes out to be 3.5 volt. Okay. So the sum is solved. We just, in this case, your V output is directly connected to V minus. So we know for sure that V minus is V output. That you don't need to have any doubt in that. Then you apply virtual ground concept, and then you apply KCL at this one. So one thing,
Yes.
in any network, you have to have, it should satisfy KCL and KVL. So that is something you must keep in mind, that it cannot be violated. Okay. And so I apply KCL here, but I am ignoring this current. It is very minimal. Okay, it is 0. Okay, so KCL is still true, and you must know what are the assumptions and what you have to do. Okay, but KCL and KVL, they cannot be violated. Okay, this is off topic, but what is the range of probability?
0 to 1.
0 to 1. So if a student comes and tells you that I'm getting answer 1.1, you know for sure that the student has made a mistake. Okay. So if you solve something and then you check KVL and it is not matching, then you know you have made a mistake. You have made some error somewhere.
Yes.
So this is question 7. So this also how will be solved.
Same pattern.
V
Okay.
plus will be 4 volt.
So V plus is 4 volt, fine.
And current going through 2K is half ampere, half milliampere, sorry.
Okay, so this actually is your V plus. This is some current I. The current I is actually V plus minus 3 divided by 2 kilo ohm. So I is actually 4 minus 3 divided by 2K. That is 0.5 milliampere. So what will be my V output?
Six volt.
Mm-hmm.
6 volt.
6 volt, okay. What about others? So your V output is equal to, so this current, here current is 0. So here again current I only is flowing. So your V output is I into 4K plus 3 plus I into 2K, right? So that means your V output is what? 3 plus I into 6K. So that is 3 plus 0.5 into 10 to power minus 3 into 6 into 10 to power 3. So your V output is 6 volt. Any questions in this?
No.
No, right? Okay. Now,
Five volt.
oh, like this answering this way, see. So this is your V plus is 4 volt. Your V minus is equal to V plus is 4 volt. So 4 volt plus 1 volt, so your V output is equal to 5 volt. Right?
Yes.
I don't need to solve. It's like by observation also we can tell what should be the value. Okay. Okay. So you guys join using mobile or laptop?
I'm using that.
I'm also.
Okay, Bharat? Beautiful answer. So question 9. We have V plus is 0 volt. That means your V minus also is 0 volt. Then I will like proceed now.
We can apply KCL at negative terminal.
Okay, I apply KCL. So current flowing in is current flowing out. So what I will write?
1 minus 0 by 2k, that is half milliampere,
Okay,
is equal to 0 plus 3 minus V naught by 4.
okay.
Yes,
Okay.
AK gets cancelled out.
So this becomes 1 is equal to 3 minus V output by 2. So that becomes equal to 2
Then
is
it
equal
equal
to
to
3
5.
minus V output. So V output is 3 minus 2. So V output is 1 volt. Right?
Yes.
Okay, so barely 2 minutes. You solved it. So this is like very simple. So once you understand what are the assumptions, what are the requirements, then it becomes very easy. Okay, so now we go to question 10. Ah. Now how will you solve this?
We need to find out the V positive terminal voltage. That is one way.
Okay.
And in order to find out that, we need to know the current flowing through that top 1 kilo ohm resistor.
Okay.
For that, maybe we can apply KVL in that loop. So 1 minus 5 by 2k will give us current flowing through that.
So you apply KVL here. So you have
Yes.
this current I is equal to 1 minus I.
5 by 2k
How much is that?
minus 2 milliampere.
It is minus 2 milliampere. So what is my voltage over here?
1 minus 2 minus 1.
V plus 1 minus
Minus of minus, right? So minus
it
2
is 1
milliampere
kilo ohm
into
into I, right? So it is 1 minus 1 into 10 to the power 3 into minus 2 into 10 to the power minus 3.
so
So it
1
is
plus
1
1.
minus 1 plus 2. So it is 3
Yes.
volts.
Yeah.
So your V plus is 3 volts. What is your V
And
minus
V
then?
3 volt.
So you got your V minus also is equal to 3 volts. Then what will do then?
KCL at V minus.
Then you apply KCL at V minus. What you get?
3 minus 5 by 3
Okay, let's do V minus 5 by 3K E
is equal to outgoing current
Hmm.
V minus V out by 4k.
No, V minus 5 by 3K also is outgoing current, right?
Both are outgoing. Yes, yes. Yeah. Plus minus we can write it, or else V naught minus V dash, we can write it.
Now we'll write it there. So this is V minus V output by 4. Okay. So 0.
Hmm.
So you have V minus 5 on 3 into 1000. V minus 4 plus upon 4 into 1000. Right? Now 1000 we cancel out. It is V minus 5 by 3 plus V minus V output by 4. 0. So we get 4V minus 20 plus 3V minus 3V output is equal to 0 upon 12 is equal to 0. So you get 7V minus 20 minus 3V output is equal to 0. So you get 3V output is equal to 7V minus 20. What is your V minus?
3 volt.
So that is equal to 1. So your V output is equal to 1 by 3. That is
3.
0.33 volt. Okay. Yeah. So congratulations. You guys have solved it so fast.
Sir, I have one doubt actually.
Okay.
You said both the current are leaving the terminal, right? It is because the -5 is grounded. What was the reason you said both the current will be leaving?
No. See, it is just a convention of KCL. What KCL says, the sum of the currents flowing in is equal to sum of the currents flowing out. So when I solve KCL, what I do is I consider all the currents are flowing out. So it becomes easier to write the equations for me. That is a practice I follow. It doesn't mean, see, if I say I apply KCL and I found out that what I applied KCL that a current is going like this and current is going like this. Is it wrong?
Yes.
Might actually be the
No.
current is going in this direction. Only thing I'll get a sign which is the opposite.
In the negative. Yeah.
That doesn't mean that it is wrong. Okay. This is just what direction I've selected is different. So that will not create any issue. So there's no hard and fast rule that I must know that a direction of current is this only. And then if I use that direction, then only my answer will come correct. It is not true.
Yes, sir.
Yeah. Then what are the queries?
I missed the first few questions. Maybe can we see if I don't want you to re-explain them. Just want to see them. That's all. Okay.
Question 1.
Okay. V naught is equal to, okay, it is open circuited because current flowing out is 0. Okay.
This one.
This is summer. Okay.
Just application. Over here.
Potential divider. So it will be like 2, 3 by 4, 3 by 2. So we will substitute that 3 by 2 over here.
So, yeah.
I think from here onwards I was there. Okay. This 3 volt. 3 volt anyway. The bottom side will get 3 volt. So potential divider, if we take V naught into 5 by 9 equal to 3 volt.
Yeah.
27 by 4.
Sorry?
So we'll get 4 over here. V naught into 5 by 9 is equal to 4. V naught into 5 by 9 is equal to 4.
Okay.
So 36 by 4, I think.
No, it is kind of 5.4.
Yeah. Just can you scroll up?
Yeah.
V naught. Yeah, V naught into 5 kilo ohm by 9 kilo ohm, right? So that is like V naught into 5 by 9 is equal to 3 volt. Input is 3 volt. Okay.
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 9 by
Then
5
15 by 4. 15 by 4 it will be.
Okay.
So that is like 5.4. Yeah. 15 by 4. That is. Oh, it is not matching. Right?
15 by 4 is 3.75. No?
V naught into 5 by 9 is equal to 3. 9 into 3 is 27. 27 by 4.
27 by 4 is matching. 27 by 4 is 5.4.
9, right? 9 into 3, 27. 27 divided by 5.
27
Right?
by 4 is also not 5 point.
Yeah, it is
6.1.
5.4. 27 by 5 it is. It is not 4 actually. 27 by 5
yeah.
we need to
Yeah,
check
that is
Yeah, 27 by 5. Correct.
potential divider, no? So we should have to have the top side 5 kilo.
Yeah.
I mean, I am not calculating on paper, so roughly I'm calculating it.
Yeah. That's true. Okay.
And do we have any problems where both feedbacks are present, like negative and positive?
They have not shown actually. Currently, they have not given, and that would be difficult because then you will have to know which feedback is dominating. In case your positive feedback is more than negative feedback, then you cannot apply virtual ground concept. It cannot be applied. If you see in
Okay.
all of our networks, all the questions which we have done, only negative feedback is there. You see, if you see question 10, negative feedback, question 9, negative feedback, here also negative feedback. All are based on a concept of negative feedback. Here also decide a negative
So,
feedback.
in which cases virtual shot is not applicable? In what scenarios? Virtual shot is not applicable cases. Like in what cases? So they said like ideal amp,
Uh,
but in some cases we should not consider that as ideal amp, right? Like virtual shot. So is there any condition?
mm, to what I remember, when it becomes unstable or positive feedback is there, then you cannot apply that concept. But I'm
Okay,
not exactly sure actually.
let's consider that this V naught is connected to the positive side, right? In every one of the negative feedbacks, right? We will try to see one problem that, because I have one problem with positive feedback actually, so I am unsure that whether I can apply virtual shot there or not.
I don't think you can apply because um, with positive feedback, I'm not sure whether you can
Okay.
apply. Maybe we can check. Suppose, let's assume. Okay, this is the case. We need to have some history. I don't know if you can apply.
Okay, similar type of question only. Just the resistors numbers have changed. That's all. The input supply for the negative, that is 2.5. Okay, instead of what you have considered 2, and and negative side is 1 volt actually, 1 volt, and 2k potential divider. That's what they are doing it in that
Okay, okay.
particular. Okay.
Okay.
So that is for the negative side. Your input is 1 volt, and you have 2k and 2k in parallel actually. So that is like potential divider network. So negative feedback input, negative side input is half volt. It is going.
Okay.
Okay.
Okay, fine.
And positive side, the supply voltage is 2.5, and resistor is 2k, 2k. Feedback is also 2k.
Okay.
Bottom side 2k, 2k. So whether can we apply that virtual shot or not, I'm unsure about that in the positive feedback. because when there is a negative feedback, then we'll try to minimize the difference between those two.
Yeah,
Right.
yeah, exactly. Whether positive feedback is destabilizing, we don't know. Like I have done long ago some silent key low pass filter or silent key filter. In that, it had a combination of both negative feedback and positive feedback. And because it had a combination of both negative feedback and positive feedback, it is only valid that it is only stable under some particular condition. So that's why this one I cannot tell. I don't think I can tell. What I'll advise is you can either simulate it. You simulate it and check, then you can be sure that whether you can apply virtual concept or not.
Here we have options. Maybe we can try to check that by applying them also. I have
Okay.
options over here. So that is easy for me. Okay.
Oh, this is like what you have for this question?
This is some exercise problems, right? Not in our assignments. It is outside problem.
Oh, okay. Okay.
It is outside problem. I mean, it is not scope of our
Yeah, yeah,
course,
this
I think.
no, I don't think it's in the scope of this course because very simple. Even filters also they are not taught. High pass filter, low pass filter, all that they are not taught actually.
I think maybe in analog circuits, how we can use this network analysis, right? KCL, KVL problems. So not to introduce that concept, maybe they might have introduced these op-amps also.
In which in analog circuits.
Yeah, analog circuits, we'll be
Yeah.
using networks, right?
Yeah,
So
yeah.
this KVL.
Hmm.
So introductory part for that purpose. I don't think so. We'll be getting some questions from this chapter
Oh,
in the exam. In the exam.
if you get it's good for you, no?
Yeah, but by seeing the patterns, right? I don't think we'll be getting very easy paper.
Oh, gotcha. Anyway, I don't think it should be an issue for you guys. You guys are solving, studying, you guys are attending
No,
sessions.
no, I see some problems, right? At that particular time, we should be having that idea where how to solve it. If we struck somewhere, then we are gone for
Yeah,
that
yeah.
problem.
Anyway, one thing in these MCQ tests and everything is you should target the easy questions. What you know, you must solve. You must not
Yeah,
be like very proud, arrogant, saying, I am very wise and clever in this question. How can I not solve and get stuck over there and waste your time?
it is a waste of time. Yeah.
You know
No,
what is
no. The problem is here. The question paper is not a MCQ or MSQ now. I think it is all are fill in the blanks. Looks like to me.
Acha. Okay. Okay, even if it is number type answers, then
Because the fractional plus minus change also will give us no marks.
yeah, yeah, I mean, but the tolerance is 5% or 10%. So that should not. So like
No, no,
when
no.
I
I'm saying that v naught plus one instead of that v naught minus one. If you have taken,
then you're
then the
gone.
range will be different. Then the,
Yeah, if you make a mistake, you're gone. Even if you are doing correctly, I'll recommend you using. Suppose you got V output is 11/9. Okay,
Mhm.
you don't do use a fraction around 1.211 something and go. Use 11/9. Next time you find your IX is 10/12 V output. Then don't use 10/12 into 1.211. Use 10/12 into 11/9 and do the calculation. That's what I
Okay.
recommend. Because when you are doing it this way, you're losing some accuracy, right?
Yes.
But in this way, you are maintaining it, like you're retaining it.
And
So
if we are lucky enough, then that will be get cancelled out by these fractions also, right?
yeah, yeah,
Sometimes.
yeah. Sometimes if they are set thought and calculated and properly done and set questions, then it should get cancelled out because they should make your life easier. But it's not
No,
guaranteed.
if you see here, right, in our assignments, these are not like gets cancelled out. They are not getting cancelled out actually. These fractions.
Okay.
So
Yeah, yeah.
maybe we are having weekdays time. That's the reason why they might be giving that non-fraction values, like non-cancellation fraction values. But in exam, looking forward to have these cancellations.
Yeah, yeah. Because when it gets
If
Yeah,
cancelled, then
even I
you're
thought
on the right track actually.
the fourth and fifth week and all, I don't think there was nothing like this. It was just going and going. It's long values. I thought it would cancel out at some point. It just went on.
Oh,
Till the end, it was not there.
okay.
I mean, can we check? I mean, do we have any methodology to check whether the answer is correct or not, especially for the phasor diagrams where we have that angle and magnitude values, right?
Mhm.
So I got one value. I should be able to tell that whether this is correct or not. Maybe with not exactly the pointing out, pinpointing that this should be a correct answer. Maybe tentatively rough numbers, right? Figure of merits.
Mhm.
KCL and KVL, I can apply any one loop, outer loop or inner loop, any loop I can apply and I can see that whether it is equal or not. That is one way. And KCL also same thing, node branching, out currents, in currents. So then we'll come to know easily at any one particular node, let us say.
Mhm. Okay.
Then we can verify that way. But these phasor diagrams and these conventional conventional differential equations problems, right?
Mhm.
There I'm not sure. And on top of that, I have another question is we have different networks, RLC networks, right? RL and combination of R and LLC.
Okay.
So we should be able to derive these things at first place, and then we should be able to identify and remember these things, or else we cannot derive them in the examination during examination, right?
Why,
How
why,
to
why, why?
tackle them?
Why? Like,
Uh,
what do you mean RLC, different combinations and all that?
I am saying that, for example, there is one circuit in the transients, let us say. We
Okay.
have series R, so voltage supply is connected to R,
Uh,
inductor, and
for series RLC in the transient, what is the condition? For parallel RLC in transient, what is the condition like that?
yeah. So series you will be having tau is equal to RC, whereas LC conditions, LR condition you will be having L by R tau
Okay.
values, right?
Okay. Okay.
So these things we should be able to remember, right? Otherwise, we cannot derive them in the exam, and then we should be able to answer them. So I'm saying that in that direction. So we are limited, right? There are n number of combinations where LC will be in series and LR will be in the series and L will be in the parallel and C will be in the parallel. There are different cases will be there, right?
Ah, okay. Okay. Then, see, I prefer you to have knowledge of the way to derive. That is my preference.
But it will take
But
some
it
extra minute,
will take time. It will take time. That is for sure.
extra minute it will take. Yeah.
So that's why those
But
sort of target at the end.
yeah, correct. But some people like my parallels, right? So they are well, I mean, they are well remembering it, the things, right? So some formula, they will be seeing the circuit and they will be remembering the formula. But I'm not that kind fellow. I cannot remember the formulas. Only through process only I can go.
Hmm. Yeah.
But compared to him or her, to me it is like extra time, right? It is like a extra time.
Uh-huh. Yeah, that's true.
But in their point of view, if they forget something in the numerator or denominator, they will be gone. That's all. They cannot proceed.
Hmm. But in
That is
your
only the
opinion,
difference. Yeah.
yeah, everything has a pros and cons. In the, in
But
the
can we check these transient responses like differential equations, right? There are two ways. One is conventional differential and second one is Laplace transforms, right?
okay.
So I think I prefer like Laplace transforms are giving good results and faster results compared to conventional.
Yeah, that is very true. I also believe that.
Yeah. Okay. And you know their current wise, right? Differential equation wise, L into dab dt we will be writing, right? So that will be having some differential format. So when we have integral current, right? I haven't seen that integration Laplace they will be using. But for example, the current flowing through capacitor, right?
Uh,
Q is equal to CV, and if you want to have a current, right? I is equal to C into dv by dt. There is a differential, right?
uh,
But if I want to find a current through inductor, let us say.
okay.
So V is equal to L into di by dt we will be writing. I is equal to 1 by L into integral of V of t dt, right?
Yeah.
So in that case, Laplace transform, we should be knowing that integration, how to do it, right? Differentiation, we know S into f of s minus S of initial 0, S of 0, right?
Okay, depends on what you are trying to integrate. Usually, are you meaning to say in your implementation platform or just in solving sums?
solving problems. That's all. Not the platform. I'm not going to the.
Then you need to know what is your VL. That is fine. VL, if you know, then you can solve. No?
I mean, there are two ways, right? Where we can directly derive V of t, right? V of t directly, and then divided by Z impedance value, and then we'll get current value. This is one way.
Okay.
Or else, I can directly get the I of t from the circuit by KVL KCL, right? So
yeah,
if I
that I prefer. That I prefer.
okay, so current you don't prefer, only voltage between L and C. I mean, there are two conditions, right? First, we need to find out V of t in the expression format.
Okay. I say what I recommended is
Okay.
for capacitor, you consider voltage across the capacitor.
Okay.
For inductor, you consider the current through the inductor. Those are the variables you must solve with. Okay.
These kind of inputs that I require, so because for example, if there is a LNC network, right? So in that case, V across L is equal to L into dA by dt. So that is coming in terms of I, right?
Yes, yes.
And VC of t is directly we have taken across capacitor.
Okay.
So in this case, again I need to convert this I of t into V of t, right?
Yeah, we have to do. It depends, but like when we solve state space or for control systems or something, we usually consider some state variables, right? So
Okay.
those state variables, it should be continuous. Like you see, your inductor current cannot change instantaneously. The capacitor voltage also cannot change instantaneously. So we solve those differential equations for these variables. We do not solve it for IC of t. We find IC of t as a function of VC of t and as a function of IL of t. So we originally find IL of t, we originally find VC of t, and then we find the capacitor current as a function of these. Okay, so no matter what is the circuit, it is recommended, at least by me, that you must use the inductor current and you must use the capacitor voltage. I think I taught it also in one of the sessions. I think for transient response, I'm not sure actually.
And what about this transient? Let's say one circuitry, okay, which is having a DC source, and then it is connected to some series inductor, and then it is connected to two parallel resistors. Okay.
Okay.
And in between the resistors, we have a switch.
Okay, very good.
Okay. So before that circuit in the steady state, so L is short circuited, and we have some current. We have some current which is flowing through that. Now immediately if we switch on the switch, right? If we turn on the switch, then current will be flowing through the second parallel resistor also. Okay. But that inductor will not allow the sudden currents.
Yes, correct.
Okay. Then what is the voltage across both the resistors?
All right. So let me draw your circuit. You have voltage source, assume 10 volt.
Yes.
You have some inductor 1 Henry. You have some R1, let us say 10.
Grounded. One side is grounded anyway. Okay.
R2 is 20 ohm. There is a switch here. And then this is connected to ground. Right?
Yes.
This is your setup.
Yes.
So your initial IL of 0 initially was 10 by 10.
1 ampere. Yes.
That is 1 ampere. Now you close the switch.
Yes.
You are closing the switch at T0 minus or T0. Okay.
Yeah.
So what will happen? Your current over here was 1 ampere, right?
Yes.
Now you're suddenly closing the switch. Now you're confused. What will be the current through the resistors, right?
Yeah. Voltage across this branch, both the network R1 and R2 parallel.
So,
so it should be same between them.
The voltage will be the same.
Yes.
So the voltage across these two branches will remain the same. If the voltage across these two branches are the same, what does it mean? it comes effectively as IL of t into R equivalent, which is your 10 into 20 divided by 30. Okay.
20/3.
So that is your voltage which comes over here.
Now we need to find out IL of t.
Yeah, you need to find IL of t. So IL of t, there's a simple formula. You have IL of t is IL of infinity, right?
Yeah.
Plus
IL of
IL
infinity plus IL of 0 minus.
into e raised to minus t r mu r effective mu upon L. This formula is there, right?
So is this condition is valid for all the circuitries? Like, is there any limitation of this current?
To my knowledge, when it is a first order thing, you can use that. Second order and all, it becomes complicated. Second order, this is not valid.
Okay. Second order is not valid. So for example, if we have one more capacitor,
Then you are in trouble. So that's why when you
in the,
go through all those things, you go for simple Laplace transform. Go to Laplace
okay.
transform, consider all the initial conditions, and you solve it. That is best.
Okay. So can we solve this quickly with the Laplace transform maybe with the capacitor which is included in parallel? Let us say
The best in parallel where over here.
uh, after series resistors. Let us say.
No, if you
I mean,
okay. So suppose we have
yeah,
uh,
there.
suppose we have a capacitor over here, right?
Yes.
If this
Then
was
initial current is 0.
ah,
Initial current is 0.
and this voltage will be 10 volts. Okay.
Hmm.
That we'll have to consider. So if this is 10
Yes.
volts,
Hmm.
then what happens? Your effective network is L, so SL. What is 10 now? What is 10 parallel 20? You guys calculate.
20/3.
Assume we use 1 farad, okay, to make it simple. 1 by S. And this will be plus or minus 10 by S. Okay. This is the initial voltage.
Okay.
And this is also plus minus 10 by S. So
We are considering this as unit step, right? The DC supply.
yeah, this DC, yes.
Okay. What about AC? AC, we have to consider that e power j omega plus e power minus j omega t by 2. That is
Yes,
like
yes, yes,
sine
yes.
or cos. Sine or cos.
Based on that. So
For example, if they didn't give anything, then should I consider sine? Let us say they have given only AC supply without any conversion of sine or cos, right?
then I
RMS
don't
voltage.
then I don't know. I can't say actually because I'm not setting it. So,
Okay.
like,
RMS voltage of 2 volt, let us say if they're given, then we cannot apply this Laplace transform because we don't know whether it is sine or cos.
then in that case you must use phasor. Phasor
Okay.
concept you must use. Okay. Then you must use JL, J omega L, 1 by J omega C, etc.
Okay. So you mean to say when they are not giving in that direction, then we cannot apply that Laplace transform directly.
Yeah.
And so this voltage sources, if they are
Those
not
cases,
giving
they
proper,
want in those cases they only want your RMS voltage across capacitor, or RMS current they want. They don't want the phase information, right? So then it is not required. If you have the RMS value of your voltage, you can get the RMS value of your other things as well.
okay.
That phase is not required.
I mean, in this case, if RMS voltage is 2 volt, in that case, the input source is maybe combination of sine and cos also. It can be
Combination of
sine and cosine, right? It can be.
can be, yes.
It can be. Okay. So that's the reason why we should not consider whether it is sine or cos. Okay.
We don't know what
Okay.
is we don't know what is the
We don't
phase.
know.
Phase is not known. You know the RMS value. Okay. Then R Suresh Babu is asking like how to solve numeric answer things. So my recommendation is you must prefer to keep it as fractions instead of writing this as point whatever. Okay. Instead of writing it as 1.9 something, prefer to use it as in terms of fraction. So if you want to find if your Vx is 10 by 11 and your IL is 9 into Vx, then you know it is 9 into 10 by 11. and then you solve. So numeric answer types, you prefer to keep it in terms of fractions and solve. Okay. So I'll end today's meeting. You have to
Sir,
go for-
actually, I just want to say one thing.
Okay, tell me.
The last two, I don't know, this is not about me, but I don't think you uploaded the notes for the last 2 weeks.
Last 2 weeks. Last week I
Yeah,
didn't
10 and 11. 10
Okay.
and 11 is not.
Okay, actually the issue is I am using my laptop for these sessions, and then the videos and all I'm checking it in the PC. So then this I've forgotten to upload. Okay, I'll upload it.
No issue, sir. But I just want to just refer something. I'll just do it.
Okay.
That's all.
Okay. Okay then.
And the Thursday's meeting also will be having 2 hours, right?
No, that is 1 hour.
Okay.
Anyway, tomorrow also you have a summary session. I think it's from 7 to 9, 7 to 8. Mine also is from 7 to 8. So tomorrow you have one session. Teja will conduct 7 to 8. And day after tomorrow I'll have a session 7. Okay.
Our session is day after tomorrow, right?
Yeah, my session is day after tomorrow. Teja's session is.
Yeah, 18. Yes.
Okay then. Good night.
Thank you.
Okay.
Good.
Thank you very much. Thank you very much.
Thank you.